Here, we want to compute a line integral, right? Where the vector field we want to integrate is e to the minus x, e to the x, e to the z, right? And the curve we want to integrate it over is the boundary of the piece of this plane which lies in the first octant, right? So that this plane kind of makes some sort of a triangle in the first octant. So that means C is a triangle. And then if we stand pretty high up on the z-axis and look down at it, we should see a counterclockwise orientation on that. All right. So we could compute this integral directly, right? It might be a bit of a long haul though, because, well, the boundary of that's a triangle, right? And that has 3 pieces. Not to mention, well, actually, it probably won't end up being too bad, but there's a bunch of exponentials here. And then you have to parameterize those 3 line segments, and, you could do it. It won't be, like, really, really bad, but it's going to take some time. Instead, let's use Stokes Theorem. So, first things first, let's kind of just get a quick sketch of what this looks like. Right? So, if we draw our usual axes here, right, we can see that, well, what are the points that it intersects these 3 axes at? So, on the x-axis, if y and z are 0, then x is 1. Right? On the y-axis, if x and z are 0, then y is 9. So 1, 2, 3, 4, 5, 6, 7, 8. So we got a point here and a point out here. And then on the z-axis, if x and y are both 0, then z is just 1. Right? So that curve C is given by connecting these guys. Right? So this is C. Now what's the orientation on that? Well, if we look down from above, we should see counterclockwise, which goes this way. Okay? All right. But we want to use Stokes Theorem on this and fill in that triangle. Right? So let's say we fill that in now. That filled in triangle, right? So S is the triangle that we filled in. Okay? Now what should the orientation on S be? Right? We need to, should it be upward pointing or downward pointing? Well, hopefully you're thinking it should be upward pointing. Right? Because if we walk around this boundary with our head pointing in the sort of positive z direction here, then the surface will always be on our left. So we're looking for an orientation which is upward. Right? Okay? So we want an upward orientation on S. Right? So, well, let's just get down to it. What's the first thing we need to do? Well, the first thing we need to do is actually parameterize S. Right? So this one won't actually be so bad to parameterize, because if we look at this equation here, one variable is really easy to solve for. Right? So 9x plus y plus 9z equals 9, this is the same. Well, this can be rearranged to be y equals 9 minus 9x minus 9z, which even more coincidentally, if you like, is 9 times 1 minus x minus z. If we solve for any of the other 2 variables, which we could do, we'd be dividing by 9s. And don't really like a 1 over 9 if you can avoid it. All right, so what should our parameterization be? Well, so this implies we can use R of, let's say, UV, or actually, let's leave off the UV and just call it the two variables that aren't the two independent variables there. So we solved for y in terms of x and z, so let's parameterize it in terms of x and z. So x is just x, y is 9, 1 minus x minus y, right? And z is just z. You know, this might look better as just 9 minus 9x minus 9z. I've decided. Right? And then just z. But now you ask, okay, what is the domain of that parameterization? Well, the domain of it is just the region, the shadow of this in the xz plane, right? Because we just want the different x and z values that it can vary over. Well, so if we draw that out, here's x and here's z. Remember, it intersects at z equals 1 and x equals 1. So the domain, and it's in the first octant, so x and z can never be negative. So the domain is actually this guy right here. This is D. This guy on the inside here. Right? So it's the, in other words, the domain is, if you want to describe it in kind of set notation, it's the set of x and y where, well, oh sorry, not x, y, x, z, sorry. So the set of x, z, where both x and z are non-negative, and x plus z is less than or equal to 1. Right? So that's this triangle here, which is the shadow of this guy in the xz plane. Okay? So that just means, you know, this is the line x equals 0. This is z equals 0. This is x plus z equals 1. All right. So we've parameterized the surface now, that triangle that fills in this. So in other words, it literally is just the piece of this plane that sits in there. Okay? All right, so now we need to use Stokes Theorem, which means we need to, oh sorry, we're still finding the orientation. Right? So let's take the derivatives of this guy. Rx is 1 minus 9, 0. Right? Ry is 0 minus 9, 1. Wow, I keep thinking it's y. It's z. All right, so I have Rx and Rz. Now we have to figure out which one of these orders to take the cross product in is going to give us a positive, an upward direction. Well, remember what I was saying before, we can literally just take a cross product in any order we want, and if it doesn't get the result we wanted, then just switch it to the other one. So let's check Rx cross Rz. All right, let's see what happens there. So if we do this cross product, we get negative 9 minus 0. We get 0 minus 1. And we get negative 9 minus 0. All right, so Rx minus, or sorry, Rx cross Rz ended up not being the right order here. Okay, so because we want positive z, so let's say k component is not positive. So instead we use Rz cross Rx, right? And that one literally is just 9, 1, 9. We just multiply this by negative 1. All right, now to use Stokes' theorem here, we now have to curl f, right? So the curl of f Let's compute that over here. So f is e to the minus x, e to the x, e to the z. Del x, del y, del z, I, j, k. All right? Wow, these exponents kind of really trailed up there, didn't they? All right? So e to the x, e to the z. All right, now we want to integrate that, or integrate. We want to take the curl of this. I keep getting ahead of myself here. So d dy of e to the z is 0, minus d dz of e to the x, which is also 0. All right? Then we have d dz of this guy, which is 0, minus d dx of e to the z, which is 0. Then we have d dx of e to the x, which is just e to the x, minus d dy of e to the minus x, which is 0. So the curl of the vector field is literally just 0, 0, e to the x. It's pretty good. Right? So now we just have to integrate that. Right? So let's go ahead and find one more thing that we need, which is going to be the curl of f, right? And then we have to plug r of xz into that, right? Well, the first two components are, of course, 0. The third component is e to the x, but the x component of this is just x. So it's just e to the x. Okay. So now is where we use Stokes theorem. Right. So this line integral became this double integral over the surface S of curl f dot ds. Right? And this will be, so we need to take the dot product of curl f with the parameterization plugged in and this guy. So the dot product of this with this is really just 9e to the x. No big deal. Right? And then we have to integrate over the domain of the parameterization, which is this guy up here. So it doesn't matter the order. Let's say we do dz, then dx, just to make it quick. Right? So z here, z goes from 0 to 1 minus x. I just realized this isn't going to be as quick as I thought. And then x is going to go from 0 to 1. Yeah, this actually isn't going to be as quick as I thought. All right, so when we integrate this with respect to z, it's from 0 to 1 minus x. So this becomes the integral from 0 to 1 of 9, 1 minus x, e to the x dx. All right, so this involves integrating x e to the x. So let's just make a, we haven't done integration by parts anywhere in this series of videos so far. So let's just go ahead and do one real quick. Because, oops, I should have double checked that before we did this. So let's just remind ourselves how to do this. X e to the x dx. This is integration by parts where we use u equals x, dv is e to the x dx. Right? So remember, integration by parts is uv, so we need to integrate this for v, which is just e to the x. So here's uv, and then minus v du. So minus integral, well, v is just e to the x, du is just dx. So the integral of x e to the x is x e to the x minus e to the x plus c. Okay? So there's your little throwback to Calc 2. All right. So we integrate this. Let's pull out the 9. And we get e to the x from integrating the 1 times e to the x. Then minus all this stuff. minus x e to the x, so minus this minus is plus e to the x, from 0 to 1. All right? So that gives us, so plug in 1 everywhere here, and we get e minus e plus e, so 9e, right? Now plug in 0, we get 1 minus 0 plus 1 plus, minus 18. So the answer is 9e minus 18. All right? So that was on accident. We weren't actually supposed to, I was trying not to pick an integral with integration by parts. But still, you know, this still ends up being much nicer than doing 3 line integrals. All right? So hopefully you've seen now how to use Stokes Theorem in both directions, switching a surface integral or a flux integral to a line integral, and now switching a line integral to a flux integral. Right? It can go either way, and you know, hopefully that all made sense. And there's one more cool trick I'd like to show you with Stokes Theorem. So see you in the next video.